So anything else from homework stuff?
7-1, like number 6. Are we just drawing the angle?
I think so. Hold on, let me see. Yeah. Yep, so you just sort of eyeball it. Yeah. You don't need to buy a protractor. Yeah, but you should be able to eyeball that sucker. Yeah. So all of those problems, 7-1, 6 through 21, you just eyeball where they are.
Are we going to use one at one point?
So again?
Are we going to need a protractor at one point?
No. It's not geometry class, even though we do a lot of geometry in here. Anything else from homework stuff? Yes? Yeah, all right, perfect. What was the one I was gonna do? I think it's there, yeah, that's the one. Okay, so maybe this is good. I was gonna do a problem sort of like this. Maybe this will be the one I do. Let's see. So let's see, it tells me that a bike has wheels 28 inches in diameter. The tachometer determines that the wheels are rotating at 180 revolutions per minute. Find the speed the bike is traveling down the road. So can somebody help me out? What would the variable be, right? Like R is the radius, D is the diameter. What would the variable be for this 180? What is this value? Like if they told me the radius is 7, then R is 7, right? And wherever I see an R, I'll put a 7. What is this? What's the letter? Say again? Yeah, the curvy W, right? So this is a speed, but it's how quickly the angle is changing. So when I'm talking about how quickly my position is changing, that's V, that's velocity, right? When I'm talking about how quickly an angle is changing, that's the curvy W. This little shoo, shoo. And that just means angular speed. It's kind of crazy. It makes sense. The speed of something is how quickly it changes. So if I am revolving, what is changing? The angle that I'm at, right? So this is angular velocity. So they tell me omega. What else can I get from what they tell me that I'm definitely going to need in an equation? What else shows up in these equations? What's the equation for arc length? Does anyone remember? S equals R theta. What's the equation for velocity related to curvy W, dude? R omega. Right? And real quick, all right. We talked about why this makes sense. We developed this equation. This relates if I walk on a circle, the distance I go versus the angle that I kind of sweep out. That's what this equation tells me. And by the way, this letter is theta. It's not a 0, it's got a little curly Q at the top, right? Different fonts give you theta looking differently, but that's what theta should look like. It's the Greek letter theta, not a big deal. Right, where math people are like, we're running out of letters, let's steal some from the Greeks. All right. Okay, you guys with me? And that, pretty much every damn time you see that letter, it means an angle. Okay, how are we doing so far? So I forgot to kind of focus on that yesterday, because to me, theta is like the letter B. It's like, well, of course it's the letter B. But you guys are like, I don't know Greek. All right, so this is theta. This means an angle. So watch this, guys. S is the length that I'm traveling, correct? It's the arc length, that's how far I'm going. Theta is the angle I rotate through as I walk around the circle. You guys with me? What is this again? Velocity, and that's the rate of change of what? Velocity is how quickly or what is changing. I'll take a few different answers. What is velocity? Question. No, don't do this. Just what is velocity? I'm walking at a certain velocity. What's changing?
Change in distance over time?
Yeah, I love it. I love it. Or position, right? So I start here, and over time, my position changed, correct? Okay. Bless you. So S is kind of like where I am on the circle. This is how quickly this is changing. Stay with me. Come on, come on. This is how quickly this is changing, right? So if I speed up, isn't S going to change quicker? Aren't you going to go around the circle faster, right? So this is where I am on the circle, kind of like the length I've gone. This is how quickly that is changing over time. This is the angle I sweep through. This is how quickly that is changing over time. Isn't omega the change in angle? So think about it. If I speed up how I'm changing the length, then the angle change should speed up also. That's why this equation makes sense. How quickly I'm moving is directly related to how quickly the angle changes where I'm at. So when I'm here, the angle is this. If I move a little bit, now the angle is bigger. The speed that I'm going around the circle is directly related to the speed that the angle is changing. Okay, maybe, I don't know. So this equation directly leads to this equation. These are connected, so how quickly they're changing should also be connected. Okay. What letter keeps showing up there that I haven't identified directly yet in our problem? R. What's R?
Radius?
Say it.
Radius?
Sure, but what is the number? 14, because that's the diameter. Radius is, of course, halfway. 14 inches. Okay. So, whenever you're presented with something, and this is not a word problem, by the way. This is just a problem with words, and you just got to know what to do with the numbers. The formulas are all created for you. Are you with me? Word problems are ones where you got to make the formula. That's why those are hard. This is not a word problem. We got all the formulas we need. We just have to figure out what the hell they tell me and where to put it. So I know R, and I know omega, and what is it they're asking me for? The speed the bike is traveling down the road. What letter would that be? The speed the bike's moving. What variable would that be? How quickly I'm on the bike. How quickly I'm moving. What letter would that be? Sing it.
V.
V, of course, right? Velocity. Do you see an equation that relates what they tell me with what they ask me? They tell me R, they tell me W, or omega, right? What's the formula I'm going to use?
V equals R.
V equals R omega. So yeah, you just got to plug stuff in now. So when they give you a problem that's got a lot of words, that doesn't mean it's a word problem. It just means it's got a lot of words. You got to find the numbers they give you and identify what they are, so you can put them in the right place in the formulas. Okay. All right. So yeah, so now you just have to multiply these together. This thing here needs to be in, what is that thing related to? 180 revolutions. If I go 1 revolution, right? How far have I gone? I don't know how far the distance is, but what's the angle I've gone through?
360 degrees.
Beautiful. Now give me radians. All the way around the circle is how many radians? 2 pi. I love it. Somebody back there shooting a sign at me, right? Okay. So, if I go 180 times around, how many radians will that be? 360. One revolution is 2 pi. So 180 is 180 times 2 pi. Again, I love it. We got to get away from degrees. We're going to still use degrees sometimes, but most of the time we want radians. Why are radians better? Why are radians better than degrees? You guys remember from yesterday?
Because you can actually see the radius.
Yeah, it's a real physical measurement, right? Degrees, we completely not arbitrarily, we picked the number 360 because it was nice. But radians are real things. They take the radius and they measure the circle using its own radius. It's a physical measurement. 360 degrees, that has nothing, there's no basis in reality. We just chose it, we just picked it. Do you guys understand what I just said? Right? There's nothing special at all about 360. There's nothing special except it can be divided by a lot of numbers. That's why we chose it. We could have made it 400 degrees in a circle. Maybe. Okay. All right. So this is my omega. Does somebody remember the formula for omega? It's how quickly what's changing again? Omega is how quickly the angle is changing. What's the letter that represents angle? The new one, yeah, the little curly Q dude. This is going to make, what I'm about to say is going to make a little more sense after we do the next section. But anytime you see this guy out on its own, it's not inside a certain function we're going to learn later. It has to be radians. You don't have a choice. Do you see how he's just free? Is he inside something? No. So he has to be in radians. So coming back. One revolution, if I go all the way around the circle, that's 2 pi radians, correct? So 180 revolutions, let's do it again, would be 180 times 2 pi. Because I'm doing 180 of these. So this will be 180 times 2 pi per minute. That's what omega is. If I would have used the word rotations instead, would that have changed anything? One revolution is the same thing as one rotation. So they're going to use both words. They both mean the same thing. So I really want you guys to be with me. One revolution is 2 pi radians. We proved that yesterday. One revolution is 2 pi radians. So what's 2 revolutions? 4 pi. It's crazy. So that's all we're doing. 180 revolutions is 180 of these. So this is omega. And this is r. You can solve. So you can get what V is. So a few of these problems are really just going to be conversion problems. They tell you rotations and you need radians. Damn it, come on, problem. So then you got to just make it radians. Okay. So let's do this. This was number what again, sorry? 72? So this is 72 and 7.1. And when you do the problem, you have to, everything I've got. I mean, I explained a little bit more. Okay. But the main thing with these kind of problems is they give you information and then they ask you a question. You've got to identify what is it they're asking me, and is there an equation that relates that with what they told me? That's basically all that is. It's not a real word problem. We're not creating the equation ourselves. Okay, so let's do this. Let me keep this up here. let's say I went, what do you got, Jeff? 4/5 of a revolution, of a rotation, let's say, every 38 minutes. Okay. Can you tell me what omega is? Okay, so what does omega stand for again? Yeah, fade over time, and it's the angular speed. It's how quickly the angle's changing over time, right? You can see that from the symbols for it, right? So do you see how this is related to this? I mean, there's the angle per time, right? So what do you need to do first here? What's this supposed to be in? What units is this supposed to be in? Radians. Did I give you information to figure out how many radians it goes? Yeah, 4/5 of a rotation. What's a full rotation again? 2 pi. And we go 4/5 of that. So what do you do?
Or divided by 5?
Yeah, 4/5 of 2 pi. I didn't go a full 2 pi, did I? I go 4/5 of 2 pi. So 4/5 of 2 pi. And that would be this beautiful 8 pi over 5 number. So that's what this is. And down here I got 38. So this is radians per minute. And then you just got to throw that in the old calculator. If you do 8 pi divided by 5 divided by 38. Can somebody do that? I'm going to try to do it in my head while you do that. 0.138. Let's make it shut up. Let's see what happens. Maybe that was divided by less. It's going to be more. Probably more than that. Probably 0.14 or something. Am I way off? I'm okay if I'm way off. It's too early in the morning. What do you guys get? Don't forget to do pi, right? Don't forget to times pi. Pi! Little pi dude. Does anyone have that? Does anyone have that? All right, let's do it together.
All right.
Let's do it together. All right, so let me help you guys out. Is everybody able to find pi on the calculator? I want to tell you guys a little secret. That I don't know if you know. Anything that happens in here that doesn't make sense, you just have to say, "Hey, man, what the hell is that thing about?" Well, maybe don't say it like that. You just have to say, "Hey, I didn't quite catch what the hell you were just talking about." Again, you don't have to say it like that. If you have a graphing calculator like this, pi is right there. Right above your to the button, right? So let's see what we get. 8 times pi divided by 5 divided by 38. Okay, look, I was pretty close. I should have stuck to my guns. So it's 0.132 radians per minute. We don't have a good feel for radians right now, right? If somebody told me something was moving at 8 decameters per hour, can you envision that? No, because how familiar are we with metric? Some of you guys might be more familiar because you come from a more rational country, but those of us in America, we're the only country that doesn't use metric, so we didn't grow up in it, so we don't know it. So radians are new to us, right? Radians are brand new to us. But so that's the answer, but it doesn't really mean that much to us, correct? It's like somebody telling me that they traveled 11 hectometers per second. Like, I don't know what that means. What are you talking about? You guys sort of with me? So the big deal here was, We knew the equation for what we wanted. They basically gave it to me like this. We just had to put that in the right notation. Okay. So real quick, can you guys remind me, this distance here? What is that? Give me two ways to think about that angular displacement, that angular sweep. What angle is this? 180. What's another way to think of it? Pi. Pi is 3.14 blah, 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 right? What is this? What's this angle? 90 degrees. Also known as, if this is pi, how far? Did I go a full pi if I go just here? Oh, and how much of a pi? If this is pi, how much of a pi did I go if I just stop here? Oh, and I went, did I go all the way? No, I went how much? Halfway. So this is pi over 2. 3.14 blah blah divided by 2 is about 1.57. You guys with me? So me being a geek, when I went to a deli somewhere and they gave me the number 157, I was like, ooh, 157, because I'm a total geek. But half of pi is 1.57 roughly. What is this then? Right in the middle there. Yeah, pi over 4, 1/4 of pi, right? It's half of a half. You guys with me? So on that level, even if you didn't know what pi was, you know how to cut shit up. If that's a full pi, well, that's half a pi, and that's a quarter pi. I mean, on its own, that's very straightforward. You don't have to know trig, you don't have to know angles. You could just see that that's 1/4 of a pi. I didn't go all the way. This is about 0.76 or so of it. So where's 0.132 is probably down here somewhere. So that's how much of an angle we're talking about, right? That's 0.76, so 0.132 is down here somewhere. So that's how, it's taking a full minute to go that far. So it's not moving very quickly, yes? In fact, it hasn't even rotated the full way around in 38 minutes, so that makes sense, that it's going really slowly. Are you guys with me? Okay. A little bit? Okay. So again, we so far have defined an angle. We've talked about the various parts of it. And then we came up with some equations relating some stuff we're familiar with new stuff. Right? We all know radius. We all know that. We all know angles. But I never thought about, until this class, we didn't think about speed of an angle. If something's rotating, there's an angular speed to it, right? So that's one of our brand new equations. Okay. Yeah. Let's see, let's do this. I do want to do a different problem. Let's do one more problem, then we'll get into some new stuff. Yeah, this bicycle problem. So read this problem real quick. Now, you don't have to draw a picture, but I highly recommend you draw pictures with trig stuff, circular stuff. And just identify the parts of what they're telling me. Where am I? I'm way over there. Okay. So can somebody identify anything for me? Let me draw a circle for my bike wheel.
The diameter is 24 inches.
Good. So the diameter is 24 inches. Does diameter show up in any equations directly?
No.
Not really. I mean, we could force it in there, but what shows up more often? Not diameter, but radius. And what's the radius then?
12.
Okay, so now we know R is 12. Can anyone see a problem? Okay, real quick. What else did they tell me? What's the next thing they tell me? And what's the symbol for it? Say again? No, careful. Is that how quickly an angle is changing? Isn't that miles? So that's just how quickly a position is changing. That's just my speed. It's my normal velocity. That's v. What would make it an angular velocity? If the top unit was radians or rotations, right? Or revolutions or even degrees, right? Are you guys with me? So that would be the curvy W dude. That is just I'm moving. Okay, so that's, so they tell me the velocity is 15 miles per hour. All right. What are they asking me for? Say again?
Omega?
Good. They're asking me for the angular speed, which is omega. They want to know what omega is. Now, which equation do you think I'm going to use eventually, considering what they told me and what they asked me? You can see what they told me. They told me R and V, and they're asking me for omega. So which equation relates those things? Sure, yeah. So V equals R omega or omega R. Let me just put R omega. I like doing that better. Okay. Do you guys see? I'm right now. This is exactly what I would do if I was given this problem and told to solve it. I would draw a picture. I would identify what they told me. I would identify what they asked me, and then I could figure out what equation I'm going to have to use. Right? That's how you do it. That's how you figure out which equation to use is, what do they ask me, what do they tell me, and what relates those things. Right? Can anyone identify a problem with the units? This is another thing you got to look out for. What are the units for my speed? Miles per hour, right? And actually they want this to be in radians per minute. Yeah, okay. I'll have to worry about the second part of the question in a minute. Plus, my radius is in what units? Inches. Do you guys, you've seen problems like this before, yes? I know you have. Where the problem gives you inches and feet, and you're like, oh shit, I gotta change one of them into the other one so everything works together. So, all right, here we go. I love this problem because it involves quite a bit of conversions. What's wrong with the times that they give me and ask me? What time do they give me? Don't they give me hours, right? For the speed? And what do they ask me for?
Minutes.
Shit! So I got to change that. And they give me miles, but I also have inches. They have to agree too, or else this is never going to work. Does that make sense? Maybe. Okay. So watch this. All right. This kind of thing is going to happen to us a lot. Let's take care of the time first. That'll be easier. I don't want hours. I want minutes. Right? And how do I know that? Because they asked me for per minute, and I've got per hour. So let me change that to per minute. So what do I not want? What do I not want here? What do I wish wasn't here? Hours. So how do I fill hours? Do I put it there or do I put it there? If I put it on the bottom, I get hours squared. Right? On the bottom. I want it to cancel, correct? So where do I put it? On the top. You guys see how then it cancels? I want to go from hours to minutes, and we can go from hours to minutes. How many what's in what?
60 minutes in an
60 minutes
hour.
in 1 hour. What is that telling me to do? Divide. Okay, so let's not do that yet. Let me see if you guys can see this. This is in inches. This is in miles. right? So I need to convert one of them to the other one. Is it easier to convert inches to miles or miles to inches? What do you think? Inches to miles would suck so much. Because it takes 12 inches to make a foot, and then how many feet to make a mile? Does anyone remember? How many feet make 1 mile?
5,280.
5,280. It's a good little factoid to know. Do you guys all see what to look for in a problem? You have to look, what are they asking me for? What do they give me? Right? So which equation do I want to use? And do the units agree? If the units don't agree, that's another level of the problem you got to take care of. Okay, so far I got miles per minute here. Do you guys see that? I don't want miles though. And I don't even want feet necessarily. Can you guys see those? Is there somewhere these guys meet in the middle? I have inches here and I have miles there. Can't I change both of them into feet? So 12 inches is, holy shit. Okay, so R is now in feet. What's not in the right units yet? Miles. Okay, look. So where do I put miles so it cancels? Top or bottom? Bottom. So what goes on top? Feet. And now we know there are 5,280 feet in 1 mile. So what are you going to put in your calculator? 15 divided by 60 times 5,000. So if it's on the bottom, divide. On the top, multiply. This little conversion tool is awesome. Has anybody ever taken chemistry? Any chemistry? Does this not look familiar? Moles, Avogadro's constant, grams. Oh God, Jeff. Okay. We just kind of, well, you know, we didn't really steal it. They steal it from us, but we're going to pretend like we're stealing it from them. I don't know what the hell it is. 1/4, 4, 13, 20. Is that what that is? Does nobody help me out? Okay. Yeah, thank you. What's the units? Watch how nice it is. What unit is left alive on the top? Feet. What unit is left alive on the bottom? Minutes. This is V, correct? V is this, and we just changed it into feet per minute. So if you're going 15 miles an hour, you are going 1,320 feet per minute. Same thing. Okay. So now, what equation? We've got this equation here, right? That relates what they tell me with what they ask me. So what do I put here? What goes here? 1320. One foot, it's got to be feet, right? Times omega. So we basically, do you see what's happening? And what's omega going to be in? What units is it going to be in? This is going to, well, let's see if you guys can. What is omega? Omega is theta over time. This is going to be radians per minute, which is exactly what they want. Let's see. Is that what I got? Yeah, cool. Okay. Maybe. Look at the second part of the question. How many revolutions per minute do the wheels make? So we know it does 1320. So this is the answer to the first part. 1320 radians per minute. And they want to know how many revolutions per minute does it make. Well, what's a revolution? How many radians is a revolution? 2 pi. So every 2 pi radians is a revolution, right? Every time I go through 2 pi, I completely turn around. So how do I change 1320 radians into revolutions? Well, we can do this even. We can just do this again. I don't want radians, I want revolutions, correct? 1 revolution is how many radians? You just told me, sorry. 2 pi. So you just divide. It's just a straight up conversion. Right? Every revolution is 2 pi radians. So I'm curious, how many 2 pi radians is in 1320? That's what we got to figure out. Okay. 220, so like 210. If anybody's doing that.
2073.
What is it?
2073.
3,000?
2000.
2,000. Makes no sense. Okay. So I think what happened is you put in the calculator 1320 divided by 2 times pi. I think that's what went wrong.
Yeah.
Isn't the pi supposed to be divided also? Doesn't it make sense that it should get less than 1320 because I'm dividing by 2 pi?
210.0.
Hey, holy shit. Do you remember what I said? Sorry. I'm just excited because my brain is working this early. 210 point whatever, blah, blah, blah. Radians per, no, revolutions per minute. Radians cancel. Okay. So a little conversion grid thing is awesome because the first step you do is, we're not really math truly, you're just killing the unit you don't want. It's a beautiful way to convert things. Okay. All right.
What does the parentheses do in the calculator?
It puts this, so if you put this into the calculator, it's going to do 1320 divided by 2 times pi. It's going to do what you told it to, right? The old adage, garbage in, garbage out. I don't blame you. This is hard to forget that this means 2 times pi. You just think of it as 2 pi. The calculator is going to look at it as 2 times pi. So it's going to do 1320 divided by 2, and then multiply by pi. So you got to tell it, no, dumb calculator, that pi is down there. Right? It doesn't have eyeballs, so it has no idea where the pi is supposed to be. It's just going to directly do PEMDAS to what you throw in. Does that make sense? That's why you need to show your work. Because if suddenly an answer shows up, and so if you show your work, I'm like, oh good, you got the work right, you just put it in the calculator wrong, I'll take off very few points. If you don't show me your work, you're going to lose everything, because I don't know what the hell happened. Maybe. Okay. These are some of the more complicated problems, by the way, right? I just went straight to the last few problems in this section. The earlier problems are much less complicated. Coterminal stuff. Oh, we do have one more thing to talk about. That's why I had to finish up this section. Converting radians to degrees, converting degrees to radians, right? So the one we haven't talked about yet is the area of a sector. So real quick, does everybody understand? The problem we just did is one of the hardest problems in this section. You understand? It's not representative of all the problems in the section. Are you with me? So if this gave you some issues, okay, it's supposed to. It's not supposed to be like immediately obvious. Okay. Maybe. All right, let me bring you back. So the last thing we got to talk about, and this is where I one day I'm going to do this. I'm going to bring in construction paper. We're going to have fun. Has anyone ever seen? All right. First off, what is the area of a circle? The radius r. Say again. Too many things. What? Sorry. No. Not the angles in a circle. The area of a circle. The area of a circle. Okay. All right. Sure. All right. So let's figure out what it is. I'll work with that. I'm almost certain you guys know. You just don't want to tell me. So I'm given a circle. Here's the thing about area. If I ask you to figure out the area of this shape, would you figure out the area of the box and then the area of the triangle and add them together? Would you do that? There's no area for this shape. There's no formula for that. You would just break it into things you know and add them together. Correct? Do I want to do that? Yes. What about, all right, so what's the area of a triangle? So given some triangle, you guys remember the area of a triangle? What's happening? What's the area of a triangle? 1/2 base times height, right? Half height base, no trouble. Okay. So 1/2 base times height. Right? Why does that make sense? Because the area of a rectangle is base times height, right? And of course, half of that is a triangle, correct? And of course, you could do parallel or whatever. So, okay, that's the basic idea why the area of a triangle makes sense. It's base times height, but it's half of the associated four-sided deal. Does that make sense? Okay. Yeah. You guys just don't want to talk to me. It's okay. I know you know what the area of a triangle is. I get it. I think so. Okay. So what about the area of a trapezoid? Shit. All right, so let's see. Do you see how it has two bases? Could I turn this around and it would still sit there? It would still sit on a table or something, right? So I'm going to call this base 1, I'm going to call this base 2, and this is the height. So watch what I'm going to do. To figure out the area of this, I'm going to break this into two triangles. You guys see the two triangles I just made, right? So here's one of them, and here's the other one. What's the area? So we'll call this the second triangle is the first because it's got that base. What's the area of the second triangle? What's the height of it? Second triangle. How tall is it? H. And what's the base? B2, right? So it's half base times height, correct? Is that cool? And then I'm going to find the area of the other triangle. And it's the same idea because it is H tall. How tall is it? It's H. That's how tall it is. And its base is B1. So the area of this triangle is 1/2 B1 times H. It's just two triangles, correct? That's all any trapezoid is two triangles. So what's the area formula for any trapezoid then? Just add those together. So if I add those together, I get half B1H plus half B2H. Do you see how they each have a half and they each have an H? This is 1/2 height times B1 plus B2. Doesn't that look a lot like the area of a triangle? Half height base. But a trapezoid has two bases, so you just add them together. So the basic idea of area, if I'm presented with some shape I don't know, I try to cut it up into little sections I do know and then add them up, yes? So we're going to do exactly that to a circle. I'm going to make a circle into a rectangle. Okay. So if I'm given this circle, I'm going to just cut it across the middle. I'm just going to cut it. So I got two semicircles. You with me? Okay. Then I'm going to cut from the center out like this. But I'm not going to go through the edge. I'm going to cut from the center out, but not through the edge. Anybody ever made those paper angels or whatever the hell they're called? You know, where you open them up? Maybe? Okay. So watch this. So I chop the top half off, and then I cut out to the edge, but not through the edge. So then I can pick it up like this. I could pick this up and put it here. You guys see, I just open that up and put it right there. Is that cool? I know I don't have the same number of slices. I don't care. It's just the idea. You with me? So guess what I'm going to do to the bottom? The same damn thing. I'm going to chop it. Chop, 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 chop. And I'm going to open it. I'm going to shove it in there. Now the smaller I cut these, the more rectangular this becomes. Now help me out real quick. I really want you with me on this, because what is the distance all the way around? This is r. 2 pi r, right? So what's halfway around? What if I stop here? Pi r. Isn't that how long this is right here? Isn't pi r this, right? And isn't that this? Remember, I just opened it up, yes? So isn't this pi r? And what's this? What's this? R. What's the area of the rectangle? Pi r times r, which is pi r squared. There, okay, so circle area is pi r squared. Has anyone ever seen that before? Some of you guys have seen it before? Anyone never seen that before? Anybody don't want to tell me? Okay. Don't even want to tell me that you don't want to tell me. Okay. So, alright, so now we got that. We got the area of a circle, pi r squared. So what I really want to know is, what is the area, if I'm given a circle, what is the area of a slice of the circle? So it's still got a radius of r. I just want to know the area of this slice. So I'm going to do it 2 different ways. Somebody help me out. What if the angle I'm talking about was there, was pi? What's the area of this much? That's how much of the area? If the whole area is pi r squared, yes? What's the area of just this shaded piece? Half pi r squared. It's half of it, yes? So that I can just see from the picture. It's just half of the damn thing. Okay, I like it. So what if I only did this much? 1/4 pi r squared. I like it. So tell me this. What is the angle of this? What is this in radians, this angle? I know it's 90 degrees, but what is it in radians? Pi over 2. I like it. How much of a full rotation have I done if I stop here? You guys can see it, right? How much of a full rotation have I done? Have I gone a full rotation if I stop here? How much of a full rotation? What fractional part? I've gone how much of the way? 1/4 of the way, right? Okay. So in general, why does that make sense? Because I've gone pi over 2 out of 2 pi. Okay. How do I do this? Is this pi divided by 2 pi means times 1 over 2 pi? Do you see how the pi's cancel? You can actually see it here too. And the 2 times it's 1/4. Of course it's 1/4. We knew it was 1/4. But what that means is, if I go through some angle theta, the area of this, what we call sector, the area of this sector is going to be theta out of 2 pi times pi r squared. So this becomes, 1/2 theta r squared. That is the area of any sector of a circle. So for example, if I have a circle of radius 11, and I want to know what the area of a sector where the angle is, what do you got, Jeff? Pi over 3, sure, radians. Well, if I don't put any of these radians. Just plug and chug, right? The area will be 1/2 times the angle times r squared. That's it, right? That's just plug and chug. So where the hell that is? I don't know, just throw it on the old calculator. Let me see. 62.8. Yes.
Where did you get the 3 from?
It's not 62.8, it's more than that. 64. I made it up.
Oh, okay.
I have to give you that.
Oh, yeah, yeah.
If I don't tell you what the angle is, you're like, I don't know what to do with that, right? What's the area of a rectangle of lengths I don't tell you? I don't.
63.33.
Oh, it's close.
35.
63.33. I didn't give you units. 30 what?
35.
Okay. So if I said this was feet, what would this be?
Feet. No, feet squared.
Feet squared. I know areas in squared, and of course I squared that, so it's feet squared. I know areas in square units. Let me show you a way that I like better. Let's see if you guys agree with me. So if I have I'm going to draw this in a strange way. If I have a circle, the radius is r, right? So this would be r with me. What's the, and let's say this is theta, right? This whole thing is theta. Are you guys with me? So I'm kind of drawing it in a strange way, and you'll see why in a minute. So you can look at it like that. That's how I normally draw it, but now I just drew it there. Who cares, right? Does anyone remember what this length is here? What's the name of that?
Radian?
I like it, but no, not quite. Radian is something that I kind of curve and put on the circle, but this is just in general. This is an arc length. This is just an arc length. That's S. What's the formula for that? S equals
Theta? R theta.
R theta. Kick ass. So, real quick, all right, this is going to take a little bit of, we proved it, right? We proved that's the formula for the area of a sector. We proved it. I just want to show you something really kick ass. What's the area of a triangle again?
1/2 base.
Area is 1/2 the base times the height. So if I pretend this is a triangle, why is this not a triangle? Because the bottom is curved. But let's pretend like it's a triangle for a second. It would be 1/2 the base, right? The 1/2 the base times the height. Don't I get the same freaking equation? Isn't that kind of cool? So if I made a really small sector, this would be sort of straight. That's why it sort of works. Okay, that's the better proof. This one I like though. It's just neat. It's just a triangle, almost. Maybe? No? Screw you, Jeff. Okay. So we got one more, and normally, I don't know why I'm writing it like that. I normally write it like this. It's the same thing. I just put the r squared first. So if I write it, I normally write it. I have no idea why I'm writing it like that. Okay, same thing though. So one more equation to pile on that, yes, you must memorize. Oh, Jeff, you suck. Okay. That was the last thing in this section. So let me give you an example of a problem. Okay. So let's see if you identify what's wrong with this. So I want you to find the area of the sector of a circle with a radius of 6 inches, and the angle is, what do you got, Jeff? 68 degrees. It's not drawn to scale. So I basically tell you everything you need to know, it seems, but can somebody tell me what's not quite in the right format? Is there something I gotta change? Angle's supposed to be in radians, right? How do I remember that? Anytime I see theta, is it inside of, we don't even know what a trig function is yet, some of us do. Is it inside of a function, a special trig? No, it's out on its own, isn't it? Isn't that out on its own? It's not inside something. It must be in radians. If it's inside something called a trig function, it could be whatever the shit it wants to be. When it was out in the wild, it's got to be a real physical length. It's got to be radians. So how do I change 68 degrees into radians? You guys remember? We talked about it a long time ago. About 24 hours ago. Yeah, 68 degrees. I don't want degrees. I want radians. How many degrees is how many radians? 180 degrees is pi radians. 11. So you just throw that in your old calculator. To be really honest, you should just reduce this. I'm almost sure you guys don't want to, but 4 goes into both of these. 4 goes in how many times, Jeff? 17 and 45, is that right? No. Yeah, 45. So 17 pi over 45. Yeah! Not pretty, but I expected it to not be pretty. Right? So then the area would be 1/2 times the radius squared times 17 pi over 45. Now you can just throw all that shit in the calculator. Pi, 18, 19, 19 or 20, somewhere in there. Yeah.
How did you get 17?
Oh, just reduce 68 and 180. I'm pretty sure 4 goes into 68 17 times, right? Yeah. Just divided both of these by 4. Just reduced it. Right? Yeah. You don't have to be honest, but it's good to get in that practice because we're going to be doing that a lot. What did I say? I think it was around 19 or 20. I'm okay if I got it wrong. So don't hold it back if it came out different. 85? Holy shit, am I that far off? Did I forget to multiply by pi? Is that what I did? Let's see. 18, 2/5, 0.4. No, I did. Alright, let's see. Bum, ba-da-bum, bum, 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 bum. So 1/2 times 6 squared is 36 times 17 times pi divided by 45. Yeah, 21, there you go. Oh, you can't see it. Right. 21.36 or something. Did you guys all get that? If you haven't calculated. What units would it be? Inches? No? What is it physically? Area. What did I do to 6 inches? Didn't I? So 2 ways you should know the units. It's an area, so it's got to be square units. And I squared the units, right? So it's square inches. Okay. Not too bad, right? For most applications, if they give me the angle in degrees, I'm going to need to change it to radians. Sometimes no, and I'm going to try to make it clear when you don't have to, but you always can, and it will still work. In fact, it will work much more often. Okay. All right. Okay. So here's the real thing I want to talk about today. So that finishes up section 7.1. What we're getting into now is real trigonometry. So all 7.1 was sort of a laying the groundwork. What are angles? What's the area of a part of a circle? All that kind of stuff. That's not really trigonometry. So here it comes. Okay. It's kind of a big moment, by the way. Has anyone never done any trigonometry? Has everybody in here done some sine and cosine, or has anybody never done? All right, I love it. You never done trig, okay. So I really want you to remember what I'm about to say. All trig functions are ratios of sides of a right triangle. That's all they are. So, help me out, guys. If I have a right triangle, and this is 3, and this is 4, let me call this theta. Can anyone help me figure out the hypotenuse, how long that is? What's the old Greek dude that did some shit?
The Pythagorean theorem.
Yeah, Pythagorean theorem. He actually didn't do it, his followers did it, and he took all the credit, but oh well. Math's history is a little bit evil. What's Pythagorean theorem say? Given a right triangle, A, B, C, what happens?
A squared plus B squared equals C squared.
Yes. And real quick, let me show you my really quick, not really a proof, but a neat visual. I'm going to put it down here and make it a little bit smaller. You'll see why in a minute. So if I have A, B, C, stay with me, this is kind of cool. If I draw a square off of each side, so it's going to be A by A, is that cool so far? I'm drawing a square, trying to, off of each side. What's the area of this square here? A squared. What's the area of this square?
B squared.
What's the area of that square?
C squared.
So if I took that area and added it to this area, I get that area. It's a cool little video. Somebody constructed this where it holds water, and this side is all filled up, and when you turn it, so when you put this up top, these two perfectly fill up. So it's a beautiful visual proof of Pythagorean theorem. Just remember the little squares hanging off the sides, and you won't forget to square your parts. They're all about the relationship of the squares coming off the sides. So help me out. What would this look like then? Which is the most important side? Which is the most important side? Which two sides don't matter? Does it matter which one you call A or B? No. C is the most important side. And C, of course, is also known as the hypotenuse. That's right. Hypotenuse, that's correct. Right? We all know that. That's a good old hypotenuse. Right? So it doesn't matter which one of these is A or B, because I'm just adding them together squared, right? So I get C squared equals 3 squared plus 4 squared. C squared is 25. Why do I not have to put plus or minus when I do this? I normally have to put plus or minus. Of course, why do I not put it here? Because it's freaking length, right? Don't tell me you got a shed that's -5 feet by -7 feet. I ain't going near that thing. The hell is that? So this will be 5. Okay. All right, so there's going to be Pythagorean theorem running all over the place because we're going to be talking about right triangles, right? Okay, so we're going to do a lot of stuff. We're going to do a lot of stuff with trigonometry. You guys ever seen people out with the little, they set up on the tripods and they look through it and there's somebody else down way far away with a little stick they're holding? Surveyors, right? Have you guys ever seen that? And they kind of come out every now and again to see if the ground has like sunk anywhere. Anybody, you guys know what I'm talking about? Have you ever seen that? What they're doing is they're measuring angles from one place to another, some designated place, and if the angle has shifted, that means that the ground is either going down or coming up or something weird's happening. Are you guys sort of with me? That's one reason surveyors are out there. They use trigonometry to analyze. So if it's a set distance apart and they know the angle they're dealing with, they actually know all these side lengths involved. All right, so we're going to work our way to there. Okay, sorry. Just that's a real life immediate application of trig. So the trig function names are weird. The one we normally start with is called sine function. And a looks like. We just sort of, putting the E there would be too much for us. So we just shorten it down to be sin. There's sin in mathematics. The sine of an angle is just, let me see if you guys are with me. If you had to tell me which thing looks like it's the y-axis, which thing looks like it's the y-axis? Which piece of this? The 3, right? Which piece looks like the x-axis? 4. You with me? And of course, this is the hypotenuse, right? So the sine of an angle is the y side divided by the hypotenuse. All that trig functions are ratios of sides of triangles. So in this case, what's it going to be? Yeah, it's 3 divided by 5, which we can say is 0.6. Is that good? Yes.
Is it y over h?
Yes. Well, I called it C here, but in general, it's the y side divided by the hypotenuse. Is that cool? Yeah. I know I called it C. I should have called it H. But it's the hypotenuse. So I'm just trying to say in general. Yeah. And real quick, I really want you to get this. If I took this triangle, right, with this angle, okay, stay with me, and I made it, well, it's supposed to be twice as big. All right, that's roughly twice as big. It's fine, buddy. You'll be okay. Twice as big. Did the angle change?
No.
Nope. So sine of the angle better not frickin' change, or this whole trig shit can be thrown out. All of trig is stupid. We can throw it all out if it doesn't work. Help me out. I made it twice as big. So how long is this now? 10. How long is this? 6. How long is this? 8. What would the sine be of this new bigger triangle? What's the y side now? 6. What's the hypotenuse now? 10. What is 6/10 reduced to? 3 frickin' fifths. All right, so that's why it doesn't matter how big or small your triangle is, the sine of the angle stays the same. It will always reduce to be the same number. So the sine of a given angle is a number, and it's always that number. Because of this, maybe. Okay, we take that away. So it's always there in the background. That's why if I plug into my calculator, in fact, let's all do this. Anybody who's got the calculator? I didn't bring it, all of them, but do you guys see do you guys see the sign button on your calculator? There. See it down here? If you're wondering why it said sin on your calculator. By the way, I might as well tell you this right now. Do you guys see the mode button? If you have a calculator, push the mode button. You see something very crazy important for us. Do you see right here where it says radians, degrees? Okay. Holy shit. When you're doing something, quiz, a test, homework, you gotta make sure it's in the correct mode. Trust me. Jeff has taken a quiz where his was in the wrong mode and got the whole thing wrong. It was a great experience, right? So just be careful. Okay. So let's leave it in radians. So can you all do sine? I want sine of 30 degrees. I want sine of 30 degrees. So like this is 30 degrees. So I want to know what this to this is. So let's do sine of 30 degrees. But what's 30 degrees in radians? What's 30 degrees in radians. Think about it like this. What's pi again? How many degrees is pi? 180. So if I cut that in sixths, what's 180 divided by 6? 30. So this is pi over 6. So can you all do the sine of pi over 6? It's not this triangle. Don't get freaked out. I just want to, we're going to keep this banked for later. Sine of pi divided by 6. What do you guys get? A half. Okay. I love it. So just want to kind of, we talked about sine. We've got the idea. We're going to do a triangle related to this in a minute. Just bank that. So I just want to show you where it is in your calculator, what to be careful about with radians and degrees. Yes?
What is the main idea of the sign? I didn't get it.
Okay. Let's come back to that. So just bank this. Sine of pi over 6 is 0.5. Remember that for later. All sine is. Sine of an angle is the ratio of the y side to the hypotenuse. That's it. How long is the y side divided by how long is the hypotenuse? It's just that ratio. Every trig function is a ratio. How many ratios can I make? I can make this to this, correct? I can make this to this. I can make this to this. And then I can make all of those reciprocated. There are 6 fundamental trig functions related to all the ways you can make ratios of sides. Can't you make 3/5? Can't you make 4/5? Can't you make 3/4? Can't you make 4/3? Can't you make 5/3? Can't you make 5/4? Okay, 6 ways to make ratios. So there are 6 trig functions. Each one is just a different side divided by a different side. So all sine is, if the angle is in the base, the sine of an angle is just the y piece divided by the hypotenuse. Okay. Has anyone ever heard of something called SOHCAHTOA? Okay. I stay the shit away from SOHCAHTOA. SOHCAHTOA only helps you this far. What I'm trying to teach you will help you through any trig you ever see in your entire life. So if you like SOHCAHTOA, great. If you don't know what SOHCAHTOA is, even better. Okay. I might have just made some people like, I love SOHCAHTOA, Camp SOHCAHTOA, I got a shirt, this is, I don't care. Okay. So, the next trig function, so this is always what sine is, by the way, this is always what sine is. It's the ratio of this piece to this piece. Cosine, so cosine theta, is the ratio of the x side to hypotenuse. So what would it be in this case? 4/5. That's it. Right? 4/5, which is also known as 0.8. That's cosine. And then the third one that's really important is tangent of theta. So tangent theta. And that's going to be the y side to the x side. So what's that here? 3/4. I love it. You guys with me? 3/4. Now I think I want to do, let's do this. Let's see, one of you guys is working, I believe. So real quick, I want to kind of, so sine theta is y over h is 3/5. Cosine theta is x over h is 4/5, and tangent theta is y over x, which is 3/4. Okay, amazing, Jim. So what we just did, I know. So I got that written there, I'm gonna erase this here for a little more room, I think. So we got that, it's over here. Bye. The other 6 trig functions seem kind of funny, seem kind of like unnecessary, but there's actually more trig functions, but these are the 6 basic ones. The other 3 are just these reciprocated. So what goes with sine is called cosecant. Oh shit. This is sort of like a log of something. We put a little word, and that means a function, right? Log means the power, blah, blah, blah. So this is sort of related to that. CSC stands for cosecant. CSC. This would be the hypotenuse divided by y. Do you see how it's the reciprocal of sine? So cosecant of this angle, h to y, so that's just going to be 5 to 3. And here comes something, yes?
When you're doing the cosecant in the calculator, do you just do
Oh.
sine?
So if I wanted to know cosecant of something, I'd have to do 1 divided by sine. So if I wanted to know cosecant of 4, right, I'd have to do 1 divided by sine of 4. Yeah. So that kind of sucks. They only put room for these 3 basic ones, right? Be really careful. Above sine, what's it say above sine? I want you to be really careful. Above sine, what do you see? Besides the letter E. What does this mean? F negative 1. Does that mean the reciprocal? No, it means inverse. So that does not mean cosecant. To do cosecant, you have to do 1 divided by sine, because it's the reciprocal function. I love it. And again, real quick, on one level that seems silly. You already got sine, why need cosecant? Just flip the damn thing. We just want a word for it, right? But just remember, there are 6 ways to set up ratios of sides. So fundamentally, there should be 6 trig functions, because all trig functions are ratios of sides of right triangles. That's it. That's all they are. So the next thing is, let's see, this could be good or bad, I don't know. The next thing is, this is cosecant, right? The next thing is secant. It's kind of nice that there's something called secant if there's a cosecant. Like there's sine and cosine, right? Kind of go together. Secant of an angle is going to be h over x. See how that's the reverse of, or the inverse, not the inverse, but the reciprocal of this. So secant is h over x, in which case it would be 5 over 4. Yes?
And that would be 1 divided by cosine.
Yeah, 1 divided by cosine. Kick ass. If you wanted to do it in the calculator, you got to do 1 divided by cosine, because they didn't give us a secant button. Okay. And then finally, what do you wish this was going to be? Cotangent, which it is, thank God. So there's a cotangent of theta, cotangent theta. That is just going to be the reciprocal of this, x to y. So in this case, 4 to 3. Okay. Hopefully you understand. You have to memorize this. This is the basic building blocks of trig. You got to know what each trig function means. And please, dear God, don't forget this. They're just freaking ratios of sides of right triangles. Whatever the right triangle is you're looking at, if I say what's the sine of the angle, it's the y piece divided by the hypotenuse. Whatever it is. Okay, so on that note, I want to do some specific triangles where we actually know the angles. Okay, and then we can kind of make sure that all this trig shit makes sense. It better agree with what we find. Let me keep that up here. So let me try try to do a couple things at once. Might be too much, but we'll see. If I have a circle, now that's, for me, that's a really good circle. It doesn't look like Stewie's head for once. If I have a circle of radius 1, we call this a unit circle, which makes sense, because we often think of the number 1 as being a unit. It's not prime or composite, we just call it the unit number, 1. So the unit circle just means a circle of radius 1 centered at the origin. You guys with me? All right. So watch this. If I am at a 45-degree angle, right? What is that also known as in radians? Not quite. A little too far. Pi over 4. I love it. So pi over 4 is 45 degrees. Let me put that here. It's also known as pi over 4. Do you see I just made a triangle? You're like, no, you didn't, Jeff. Well, all right, I did. Like that, right? You guys with me? Okay. So if I knew, now if I could just, so how long is this again? How long is this? 1, right? Okay. Stay with me. So I want to figure out, so let me draw the situation over here. And by the way, if that's, so let me draw this triangle here. Just do it. There you go, buddy. All right, this is 1. This is 45 degrees, or pi over 4. What's this angle then? 45 degrees. And of course, how do you know that? Because the triangles, all the angles have to add to be 180. There's 90, so these have to be 90, so that has to be 45. Yeah, like it. Do we know how long these sides are? You might, but like with what I've given us, do we know what it is? No, we don't know what they are yet, do we? Right? All I know is this is 1, correct? We don't know how long these sides are. But can somebody tell me, even though my picture doesn't look like it because I can't draw worth shit, since those are both 45-degree angles, is one side longer than the other? You guys ever watch Star Trek? I'm sorry, Star Trek. I love Star Trek too. Star Wars, Return of the Jedi, when he put the stick in the guy's mouth. Okay, so what I mean by the line, and he put the stick in there. So the angle is like how much the mouth opens. So if this mouth opens just as much as that mouth does, these sticks have to be the same length. It's a long way to go for that. Okay, so this, whatever this is, this has to be the same. Do I know what this is? No, let me call it X. So this has got to also be X. You guys with me? All right. What does Pythagorean theorem say? X squared plus X squared equals 1 squared, which is 1. I love it. What is X squared plus X squared? 2X squared. Good. No X4, right? I don't see any X4s. So 2X squared. Can't I divide by 2? Is that cool so far? Right? Just solving for X. I don't know what X is. I can solve for X now. Kick ass. So then what's X? Square root of 1/2, which is square root of 1 is 1, square root of 2 is square root of 2. Can you rationalize that for me, please? How would you rationalize? How would you make the bottom not irrational anymore? Why can't you do the square root of 2? It's kind of a weird question, but why can I do the square root of 4 but not the square root of 2? Okay, that doesn't really answer the question. What's 4 got in it? It's got how many 2's in it? 2. And isn't the square root looking for 2 things? What is 2? 2's only got 1 2, correct? So of course I can't do the square root of 2. It's only got 1 2. I can't do the square root of 3, but I can do the square root of 9 because it's got 2 freaking 3's in it, right? So look what happens. What if I just give this guy another square root of 2? And of course, whatever I do to the bottom, I've got to do to the top. You with me? You're going to have to be able to do this for these. So on the top I get square root of 2, and on the bottom I get 2. Square root of 2 times square root of 2 is square root of 4 is 2, or better yet, half of 2 times half of 2 makes a whole frickin' 2. That kicks a lot of ass. So this is going to be a very important number to know, believe it or not. So now I know this is square root of 2 over 2, and I know this is square root of 2 over 2. So can somebody please tell me what the sine of 45 degrees is? Don't get confused about the letter X. Don't worry about this. What's the y side? Isn't sine y over h, right? Square root of 2 over 2, right? Square root of 2 over 2 divided by 1. So that's it. Somebody help me out. What's the square root of 2 divided by 2? Square root of 2 divided by 2. 0.707 something. Cool. I like it. Now. This triangle here, is it the only right triangle that has a 45-degree angle? Is it the only right triangle in the whole universe that has a 45-degree angle? No. Could I make a bigger ass triangle that has a 45-degree angle? Right? But like we saw before, if it's bigger, it'll still reduce to the same number. So no matter what triangle a 45-degree angle lives in, right triangle, the sine of that angle will be 0.77. Let's see. What do I get when I put in the calculator? Sine, in fact, I have to be careful. 45 degrees, I'm in radians, right? So I better put pi over 4. You guys with me? Sine of pi divided by 4. Sure enough, is 707, blah, blah, blah. 707, blah, blah, blah. Now notice something. What's the cosine of 45 degrees? Same damn thing, right? X to h, same thing. Why does that make sense? Because, okay. All right. Sine is basically, I'm going to say this a lot, so I'm just going to write this once. Sine likes y. Cosine, putting in parentheses because in quotes because they can't like anything. They're just freaking words and stuff we made up. But sine likes y, cosine likes x. At 0 degrees. How tall is the triangle if I'm at 0 degrees? See how tall the triangle is here? So if I push that down to 0, how tall is the triangle? Not. There's no y piece to it. As I increase my angle, do you see how the y piece gets bigger and bigger and bigger and bigger? Do you see how the x piece gets smaller and smaller and smaller and smaller? So sine and cosine kind of like, sine likes y. It's biggest when y is biggest. Cosine is biggest when x is biggest. So do you guys see how if I move around this, the x piece of each triangle gets smaller and the y piece of each triangle gets bigger? Where are they both going to be the same? Halfway. So that makes sense, 45 degrees. That's halfway. That's where sine and cosine are going to be equal to each other. Let that make sense. Okay. Let's do one more triangle. Let's see. I think it's everything I wanted to do here. Yes, there was something else, but I can't remember what it was. Too bad. So what if I go to, what do you got, Jeff? 60 degrees, or otherwise known as pi over 3. What's a triangle that's got 60-degree angles? All of its angles are 60 degrees. Does anyone know what that's called? Equilateral, good. Because while the angles are the same, so must the sides be the same. Is that a right triangle?
No.
So TRIG has, at the moment, TRIG would have nothing to say about this because they're built on right triangles. TRIG is built on right triangles. Trig functions are ratios of sides of right triangles. I like it. So look what I can do. Look what I can do. Well, first off, how long is each side? Does anyone know how long each side is? Well, what's got to be true? Can any side be longer than the other side? So I could do the same thing we did before. I don't know what this side is, so let me call it x. So therefore, this side is x, and this side is x. But this is not a right triangle, Jeff. Good job, Jeff. Right? So how do I make a right triangle? I just freaking... Didn't I just make a right triangle? What's this angle here?
30.
Does that jive? 30, 60, 90? Yeah, in fact, some of you guys might remember 30, 60, 90 triangles. Okay, so how long, so this is x, this whole thing is x. So how long is this? X over 2, because I cut it in half, right? Okay. Can we figure out how long this is? I want to know how long this is, so I can make all my angle stuff, right? So I'm going to have any clue as to how to figure out how long this is. Do I have a right triangle? Yes, I have a right triangle right here. Do I know 2 of its sides? Yes, we're algebra students, so I know 2 of the sides. This is definitely x, and that's definitely x over 2. I know them. Can you figure out this one then? Yeah, you gotta be careful though. What's the hypotenuse? X. So it'll be hypotenuse squared equals 1 side squared plus, and we'll just call this y for the moment. Is that cool? Because I don't know what it is. Plus y squared. Let's try to solve this for y. I want to know how tall that thing is. If I know how tall that thing is, I can make all the trig function stuff, right? I can make all the ratios. Okay, so let's see. X squared equals 1/4 x squared. Is that cool? 2 squared is 4. Okay, and what's the next step? Trying to solve for y. Yeah, subtract the 1/4 x squared. What's a whole thing minus a quarter of a thing? A whole thing minus a fourth of a thing is 3/4 of the thing. 3/4 shit. So shit minus a quarter shit is 3/4 shit. I don't know what x squared is, but I know how things work. I know a whole thing minus a quarter of a thing is 3/4 of that thing. I don't have to know what the thing is. And what's the last thing I want to do to figure out what y is? Square root. And again, we don't do plus or minus because this is a side length. That'll be weird. What's the square root of 3? I don't know. What's the square root of 4? 2. What's the square root of x squared? Okay, so that's what y is. Put right there, square root of 3 over 2x. So, help me out. What is the sine of 60 degrees? Square root of 3 over 2 x divided by x. So what's nice here? Cancel. So sine of 60 is the square root of 3 over 2. Let's check that. We just made that, right? We just figured it out. We just found, all we did was we had an equilateral triangle, we cut it in half. We don't know what the sides are, but now we know whatever x is, this is that many times x, and this is half of x. Sine of 60 better be square root of 3 over 2. Well, first off, what is the square root of 3 divided by 2? Square root of 3 divided by 2 is that. So now let's do sine. What's 60 degrees again in radians? I think it's, right, pi over 3. Look at that shit. Well, there it is. Same stuff, of course it's the same. So sine of 60 degrees, sine of pi over 3 is always square root of 3 over 2. Because if I make the triangle bigger, the ratio is still reduced to be the same thing. Okay. I want to show you, all right. What would cosine of 60 be? Oh, you're not. What's cosine of 60? Yeah, it'll be the x, this side, x over 2, divided by the hypotenuse. So the x's cancel, I get 1/2. So if I do cosine of pi over 3, I get 1/2. Cool. I know I got. Let's see, all right. What would the sine of 30 degrees be? Where's 30 degrees? I'm gonna erase this triangle here, just so we can really focus on the right triangle. Okay. Where is 30 degrees? Is it in the base? It's up there. So, can you just imagine this? If you turn your head, or if you turn the triangle, right, the angle's gotta be in the base, which will be the y side. So if I redraw this, just kind of turn this over, right? This will be x still. This will be x over 2, and this will be rad 3 over 2x. What is the sine of 30 degrees then? X over 2 divided by, so it's this side, over hypotenuse. So it is 1/2. Isn't that what we got earlier when we did the sine of 5 or 6? Sine of 30 degrees, you get 1/2. Okay, maybe. So real quick, all right. I want to do one more thing. We still have to finish up some other stuff here, right? I can talk about the tangent and cotangent and all that stuff, but this stuff is still just making ratios. But I'm gonna do one more thing that shows you the real life usefulness of this. Wouldn't that be good to know? Okay. So let's say there's this tree, right? And I walk out, let's say I walk 70 feet away from it. And there are tools that measure the angle of something. Right? So if I walk, I'm at the tree, I start at the tree and then I walk 70 feet away, and then I measure the angle to the top of the tree. It's a tall ass tree. And somebody told me, go find out how tall that tree is. And I'm like, I don't want to climb the damn tree. Shit. Because I could fall off the dang tree, and I don't want that to happen, right? So I start at the tree, I walk back 70 feet, and I do this, and I see that this is, 60 degrees. Okay. And I have to know how tall the tree is, right? So I want to know what this is. Which trig function relates the two sides I know something about and want to know something? Do I care about this side at all? I don't give a shit about that side. Which trig function relates these sides? Tangent, right? Tangent of 60 degrees equals what? By definition. Remember, tangent theta is y over x. So what's tangent of 60 degrees? Y over 70. How do I solve for y? Multiply by 70. Can you guys do this in your calculator? What is 70 times tangent of 60 degrees? By the way, make sure you're in degrees if you want to use 60, or if you're in radians, use pi over 3, right? So I can do this. I can do, ouch. I can change my mode to degrees. Whoa. And then I can just type in 70 times tangent, what was it? 60. So the tree is 121 and a quarter almost feet tall. Do you guys see that? Do you guys understand that physical? Did I have to climb the tree to see how tall it was? No. I just had to start at the base, count out so many feet, and then use my little thing that'll show me what the angle is. I can figure out how tall it is. I don't have to climb the damn thing. I don't have to chop it down and then measure it. That would suck. Right? No? Maybe? Do you guys understand the immediate practical application of this? How many right triangles show up in the real world? A lot. A lot. They're all over the damn place. So if I know what an angle means in terms of sides of the triangle, I can use that to do a lot of shit. I can do so many things. Okay, that's enough. That's enough, guys. That's plenty for today. So tomorrow, I'll bring like a little group worksheet that kind of, it's going to go over the first two sections of chapter 7, and then we'll go a little further in chapter 7. If you didn't get your updated grade sheet, just come up and see me.